Hello, you're welcome. Okay, so now we're gonna be looking at wave, okay, in this tutorial. All right, so now we'll start with the definition of wave. What is wave, right? In physics, wave is defined as a disturbance that travels from one part of a medium to another, transferring energy, okay? Any disturbance that travels from one part of a medium to another, transferring energy. Now, with the average position of the medium remaining constant, okay, is referred to as wave. Now, for me to actually illustrate this, I'm gonna use the representation of a wave. Okay. Now, a typical example is when you disturb a standing water right at one end. Let's say that's just water that is found water inside a trough, all right, or a container. Then you now touch one end of that particular water. What happens? Wave will be generated in form of ripples. Okay, so a disturbance will be created, and that disturbance transfers energy from this point. This is, let's say, this point where it is being generated, all right. So it actually transfers that ripple in form of energy from the point where it is disturbed, okay, to the other, all right, end of the medium. But at the end of the day, the medium itself remain, the average position of the medium itself remain constant. Okay, so what a wave actually transfer from one part to the other is actually energy, okay, in form of a ripple. So now this graph is used to represent a wave, as you can see. All right, so now this is a graph of a wave, and this is gonna be a graph of the, all right, displacement of wave with time. And of course, if you in this graph, right, the maximum point, okay, of the wave, the maximum position of the wave is what is known as the crest. It's the crest of the wave, and the minimum, okay, is known as the trough of the wave. So this particular diagram actually represents a wave. So example of wave, of course, is water ripple. I've actually talked about. Okay, when you disturb water that is actually, okay, inside a container, right, a ripple will be actually be generated from one part, the part where, okay, the disturbance is actually being created and is being transferred to the other part. Okay, so please take note of that. All right, so now we are going to be looking at the terms, okay, that is used in describing wave. All right, so terms used. So anytime we are talking about wave, what are the basic terms that we need to understand that is associated with wave? So we're going to be looking at it one after the other. All right, one of the very first term you need to actually get to know, okay, when studying wave is known as the amplitude of the wave. All right, the amplitude of the wave. Now the amplitude of the wave is actually a distance. All right, distance between the source of the wave, okay, to the maximum displacement, or the distance, okay, between the mean position of the wave to the maximum displacement. All right, amplitude, we are use a to represent the amplitude of the wave. All right, so for example, the amplitude of this wave is simply the distance, okay, from the mean position. The mean position is, of course, is this axis, this x axis, right? Excuse me. All right, so the distance from here to here is the amplitude, and of course it's still the same distance from this, okay, distance from the mean position to the crest is the amplitude, and of course the distance from the mean position to the trough is still the amplitude. So that distance is the amplitude, and of course, since amplitude is distance is measured, the SI unit is meters. Okay, so please take note of that. So the number two, so we are gonna be looking at another one, which of course is called the wavelength of a wave. Okay, how do we measure the wavelength of a wave? All right, now the symbol for wavelength of a wave is lambda. Now, the wavelength of a wave is defined as the horizontal distance traveled by the wave, okay, as it completes one circle or one oscillation. Now, a wave actually is actually is a vibration, okay, that's periodic in nature. Periodic in nature means that the same cycle actually repeats, okay, at an interval of time. So in a wave, you can actually picture a wave from what you see here to be a form of circular motion, right? From this point, to this point, right, is half circle, then you have half circle. So two half circle gives full circle. So a wave actually makes complete one circle as it moves from this point origin to this point, then goes again. So this is actually a full circle. So now wavelength is the horizontal distance you measure, okay, the horizontal distance that this wave actually covers as it actually complete one circle, right, or one oscillation is still the same thing. And of course it's measured in meters. For example, now you might see such question in exams, okay. Let's say you are being given a graph, all right, of wave. Let me draw that. Okay, so let's say we have this. Okay, so now you are being asked to get the number of wavelengths of this wave. All right, so how do we get the number of wavelengths? Now from this is one circle, right? So this distance from this point to this point is one wavelength. I'll start again. I'll measure from here to here, all right, is another wavelength. So from this point to this point is half wavelength. Alright, so which simply means that the total wavelength is gonna be one wavelength plus one wavelength, then plus half wavelength. Okay, so this is gonna be two wavelengths plus half wavelength. So that should be 2.5 wavelength, okay, if I'm not mistaken. Okay, if I'm not mistaken, that's gonna be 5 wavelengths all over 2. That's 2.5 wavelengths. So please take note of that. Number this number 2 time. All right, then I now proceed to the next time that is used in describing a wave. All right, so this time around I'm gonna be looking at what is known as period, the period of the wave. So the symbol for this one is capital letter T. The period of a wave, capital letter T. Now the period of a wave is actually defined as the time it actually takes that wave to complete one circle. Alright, the time it takes the wave to complete one circle. So it's measured in seconds. The SI unit is seconds. Alright. So the number of seconds it takes a wave to complete one circle. So if I should actually let's say I have a wave, let me also illustrate with graph. Of course, this is the time axis and why this is the displacement axis, okay? So if at this point this wave, let's say, is 2 seconds, this point is 4 seconds, say 6, and of course this should be 8. So if you're being asked what is the period of this wave, so all you're just going to measure the time for one complete circle. So the time for this wave to complete one circle is 4 seconds. So invariably now the period of the wave T is 4 seconds. That is the time it actually takes the wave to complete one complete cycle or one complete oscillation. I hope that is well understood. Okay, as we proceed. So the next thing we're going to talk about is we're going to talk about the frequency of a wave. Frequency. Okay, so I hope you're with me. All right. This time around, the symbol is F, and of course the SI unit is Hertz. It's measured in Hertz. Okay, or and abbreviate Hz. Okay, so now what's the frequency of a wave? The frequency of a wave is defined as the number of oscillation that wave can actually cover, the number of oscillation that the wave completes in 1 second, all right, or the number of oscillation the wave can complete per unit time. So frequency is defined as the number of oscillation, right, the wave actually completes per unit time. Number n represents number of oscillation, which of course is oscillation is something as second, right? While the t is the time. Okay, number of oscillation that the wave can cover in a unit time. So which simply means that, remember, the time it takes for this when the number of oscillation is actually 1 cycle, okay, then the time it takes for that to happen, the time it takes for 1 oscillation to actually take place, remember, that's period. Remember, period of a wave is the time it takes for that wave to actually complete 1 cycle, right? So the small letter t here is capital letter T period. So invariably I can simply say that, okay, frequency for just 1 cycle is going to be equal to 1 divided by the time, which of course is period. All right, so frequency is also can be given as the reciprocal of period. All right, so please take note of that. So frequency is measured in hertz. Now I'm still going to give you an example, okay, still based on graph. Is okay, I think that will actually illustrate it better. Let's say you still have a graph of wave, right, of the displacement of wave against time. So I have something like this. All right, so let's say this is 2 milliseconds, 4 milliseconds, 6 milliseconds, 8 milliseconds, 10 milliseconds, okay, 12, then of course that should be 14, right? So, and you're being asked to evaluate the frequency of this particular wave whose graph is shown here, right? So simple, for you to find the frequency, remember from the formula is the number of oscillation that is actually, okay, that's completed per unit time. All right, so you can decide to actually get the entire number of oscillation. Let's see how many oscillation we have here. All right, from this is 1 oscillation. Let me, at this point, 4 seconds 1 oscillation, at 8 seconds 2 oscillation, at 12 seconds 3 oscillation, and of course at 14 seconds, right, that's gonna be, is it really 14? Okay, yeah, at 14 seconds I'm having that's gonna be how many oscillation? 1 2 3 3.5 oscillation, that's 3.5. okay, so that means the frequency now is gonna be equal to number of oscillation is 3.5. all right, and the oscillation was completed in 14 milliseconds. Remember, in milliseconds I have to convert milliseconds to seconds. Okay, so you're gonna multiply by 10 raised power minus 3, or divide by 1000. Okay, converting milliseconds to seconds, you can just divide the 14 by 1000. Okay, so use your calculator to do this. That actually gives you the answer to that. So I hope that is well understood. As we proceed to the next term, okay, now we're going to look at what is known as the phase difference or phase angle. Okay, phase difference or the phase angle of a wave. All right, we use phi to represent the phase angle, and of course it's actually measured not in degrees. Okay, this angle is measured in radians. Now, what's the first angle of a wave? First difference of a wave. The first difference of a wave is the angular difference, okay? Of that wave with respect to the origin. Or let me state it, okay? Or let me define it in another way. So, first difference is defined as the difference between, all right, a wave, the angular difference between a wave that actually starts from the origin and the one that doesn't start from the origin. Okay, now I have actually been drawing the graph of a wave, okay, and in my graph, all the graph I've been showing you so far so good starts from the origin. So let me redraw that again. So these circles start from the origin. So if a circle starts from the origin, then that is normally such that particular wave doesn't have any phase difference. Okay, like this, right? So this particular wave, as you can see, start from origin at 0, right? So that simply means that from our reference point, which you call origin, that the cycle starts from origin to, then it starts, okay? Now some wave doesn't even start from the origin. So this particular wave that actually starts from the origin, the phase angle, it doesn't have any phase difference, all right? So since it starts from the origin, so the phase difference is simply 0, all right? 0 degree or 0 radians. But if this wave happened not or to start from the origin, okay, then it goes this way. Okay, this one example of a wave that doesn't start from the origin. Okay, let me draw that way. Okay, so this one example. So this wave doesn't start from the origin. Now the question is, what is actually the first angle of this particular wave? So from what you see here, discover that this wave didn't start from okay, it didn't start from the origin. It didn't start from the origin and start moving clockwise, okay, but rather it started after it has moved up to 90 degrees. All right, as you can remember, this is half circle, and of course half circle is 180 degrees. Okay, so if a wave is starting from at this point, okay, this is half of half circle, that's quarter circle. So this wave is actually starting at the point where the angular difference is 90 degrees, and of course first angle, we don't measure it in degrees, we actually measure it in radians. Now the question is, how do I convert degrees to radians? Okay, so for 90 degrees, how do I convert 90 degrees? What is the equivalent of 90 degrees to radians? Now look at how you convert. Of course, 2 pi, okay, for 360 degrees, 360 degrees is equal to 2 pi radians. So 360 degrees 2 pi radians. So in that case, okay, this for full circle. So one full circle, which is 360 degrees, is 2 pi radians. Half of full circle is just 180 degrees, okay? and that's just pi radians. So now for 90 degrees, that's gonna be half of pi all over 2. For 45 degrees, that is pi all over 4. Okay, so in this case now, this is 90 degrees, so the first angle is pi all over 4 radians. That's the first angle. And of course, if that wave, okay, in the case actually goes this way, okay, it should be understood that this wave, normally this wave is supposed to has actually skipped one full half circle, right? So if you want to mark where that wave actually started from, that means it skipped up to half circle. So this is where it started from. So in terms of phase angle, right? So I can simply say that for such wave, the phase angle in degrees is 180 degrees, all right? And of course in radians, okay, the first angle is just pi radians. Okay, so I hope that is well understood. So that is first angle. Having known that, then the last but not the least time, okay, and this one is very important, is wave velocity. All right, so the symbol we use is V. The velocity of a wave is actually the rate at which that wave actually changes, all right, its position, okay, with time. The rate at which the wave changes its horizontal distance or horizontal displacement with time. So velocity is simply going to be the distance, horizontal distance traveled, right? Okay, the horizontal distance traveled by the wave then divided by time. So since of course, you know, if I'm using v, velocity, speed, the only difference is that one is a vector quantity and the other one is scalar quantity, right? But now we know that for a wave, right, the horizontal distance we talked about that traveled by a wave is actually wavelength, right? So when the wave actually moves horizontally by one wavelength is actually okay, is completed after one cycle, and of course the time for that one cycle is actually period, right? Capital letter T. So that means V is equal to one wavelength divided by period, okay? So remember also that I have also, when we actually discussed frequency, all right, I've given you the formula that frequency is also giving us the reciprocal of period. Why? Because this particular formula can also be expressed like this: wavelengths multiplied by wavelength multiplied by 1 all over the period. So if that being the case now, so I can simply now write my velocity to be equal to wavelength, right? Then 1 all over period is frequency. So wave velocity or speed, okay, is well, I write this. Okay, let me write this as formula number 1. It's giving us the wavelength of the wave multiplied by its frequency. So that's the relationship between velocity of a wave, okay, and its wavelength and frequency. And this part of formula is very important. Why? Because every form of wave, be it actually sound wave, okay, electromagnetic wave, any form actually uses this formula, okay, to relate frequency with the speed of propagation of that wave. For example, let's look at as a typical example, radio station. Every radio station transmits electromagnetic wave, all right, in form of radio wave. And of course, they'll always transmit that at a particular frequency. So how can we actually get to know the frequency which they transmit? Let's say, okay, the velocity, by knowing the velocity, which of course every electromagnetic wave uses velocity of light. The velocity of light has a constant value of 3 times 10, okay, raised to the power of 6 meter per second. So let's say after measuring the wavelength of that wave, all right, the wavelength, the distance, horizontal distance travel per circle, okay, per circle of the wave, let's say it's given as 2 times 10, okay, raised to the power of, let's say, minus 2. So if you are being asked to evaluate the frequency of this radio station, okay, having known the velocity of to which the velocity of light, okay, the wavelength. So let's say you want to evaluate this. Of course, the formula that you're going to apply is this, so which we know that excuse me, from here now, frequency is equal to the velocity then divided by wavelength. So velocity is 3 times 10 raised to the power of 6, then divided by wavelength, which is 2 times 10 raised to the power of minus 2. Okay, so if we do this, this is going to be 10 divided by 2 is 1.5. All right, by indices, okay, this powers of 10, this is going to be something as 10 raised to the power of 6. Because of this division, that's going to be minus, all right, into minus 2. That's how we actually evaluate indices, all right. Indices, of course, this index, powers of 10 is index. So since the powers of 10 is dividing each other, okay, I'll apply difference law. So I will write the 10, then of course I would subtract the powers, loss of indices. But if you can do it with your calculator, it's fine. All right, okay, you can use the method that's convenient with you. So this is gonna be 1.5, then times 10 raised to 6, minus is plus, right? 6 plus 2 is 8. So this is going to be 1.5 times 10 raised to the power of 8. So that's the frequency. And of course, frequency is measured in hertz. Okay, so 1.5 times 10 raised to the power 8 hertz. So I hope that is well understood. All right. So we are good. We proceed. So now what we are going to be talking about next is classification of wave. Okay, we're going to look at different ways wave can be classified. Okay, excuse me. Classification. Okay, so now a wave can be classified into the as follows. Now a wave can either be classified as a mechanical wave mechanical wave. Other wave is classified as an electromagnetic wave. So it's either the wave is mechanical or is electromagnetic. Okay, so this is one classification. That's another way of classifying the wave. Okay, it's either that wave is said to be progressive. Okay, it moves continuously. It's said to be progressive wave, or the wave is stationary. Alright, number 3. It's either the wave is classified as transverse wave, or it is classified as a longitudinal wave. Alright, so let's start with the very first classification. Okay, we'll start with this mechanical and electromagnetic wave. Okay, so mechanical. Now, a wave is said to be a mechanical wave if that wave, okay, requires every mechanical wave, okay, requires material medium, all right, requires material medium for their propagation. That means they can only travel, okay, through a material medium. Now, what I mean by material medium, that's okay. Material medium is either any of the 3 states of matter. Okay, either they can propagate. They need to pass through solid, liquid, or even gas. Okay, so there must be a medium before they can propagate. All right. If there's no medium for their propagation, they can't propagate. A very typical example of mechanical wave, all right, is actually sound. Sound doesn't travel without a medium. It's either sound is traveling through a solid, or it travels through air, or it can also travel through a liquid. Okay, in fact, if you are hearing my voice now and perhaps you are not using earpiece, probably you are just hearing the voice, maybe let's say you're using phone system, okay, you are just hearing my voice from the speaker of your phone, right? It's not connected directly to your ear. So the only way that sound transfers from the speaker to your ears is that air, all right, the air around actually transmit that sound. If there's no air, sound, okay, cannot be transmitted, okay, to you, unless of course you are directly connected to your ear is directly connected to the source of the sound, probably through a headphone, right? So, and to actually illustrate this, if you possibly have actually most of those modern prism, or sometimes you get to see all those, maybe when you watch television, okay, get to see modern prism, okay, where inmates are actually receive visitors. In most cases, most of those prisons, all right, is designed in such a way that the inmates will not have physical contact with their visitors, even though they will see them. All right, so there's a kind of ceiling. They seal a demarcation between the inmate and their visitors in such a way that a glass actually forms a demarcation. Okay, so such glass actually prevent air, okay, to transmit sound from the visitor to the inmate, and that is in most cases such prison actually uses microphone. So if you want to talk to the person, even though you're seeing the person can't hear you unless you actually use this microphone. So that simply shows that without air transmitting sound, okay, that sound cannot actually travel to its destination. So I hope that is well understood. Okay, so please take note of that. So a wave can be mechanical or electromagnetic. So a mechanical wave requires material medium, okay? Unlike electromagnetic wave. Okay, so what makes electromagnetic wave different from mechanical is that it doesn't need okay it doesn't need material medium. Okay, so let me not say no material medium. Okay, that doesn't mean it doesn't pass through a material medium, but it doesn't require. Okay, electromagnetic wave don't require don't require material medium, so they don't need material medium to propagate. Okay, so we simply means that if they need to propagate, they can pass through vacuum. All right, vacuum simply means that it's actually a place that is actually devoid of any of the state of matter, solid, liquid, or gas. Okay, so they can pass through the vacuum. So that is why even though air cannot pass through that particular gas, the glass demarcation actually mentioned previously, but you can still see the person. Light can pass through it. All right, so why? Because light doesn't require. Light is an electromagnetic wave. It doesn't need a material medium to propagate. All right, it can pass through vacuum to its destination. Now I'm gonna give you, I will not just give you example. All right, one example of electromagnetic wave. I'm gonna give you all the example. Okay, all the electromagnetic wave. All right, in physics, arranged in order. Okay, now I'm gonna use this abbreviation to write all of it. Okay, so all the electromagnetic wave is actually arranged using this acronym Rayleigh's G. So the R here actually represents radio wave. Radio wave is an electromagnetic wave, of course. This is actually transmitted by radio stations. Okay, then I have the I. The I is infrared. Okay, and you get this kind of wave from phone, right? Infrared. You can just use it for just short distance transfer of data through phone. Then L is light, visible light. Okay, which of course is light we can only see. Vision is possible with light. Then of course U here is ultraviolet rays. Okay, the X is X-ray. Of course, ultraviolet rays actually comes majorly, the source is from the sun. Okay, the ray from the sun is known as ultraviolet ray. Of course, X-ray for scanning human body. Then G, which is gamma ray, a radioactive element, right? Now these are all electromagnetic wave. Then one thing about this is that they are being arranged, okay, according to their increasing frequency. So their frequency actually increases downward. That shows that gamma ray has the highest frequency. So please remember Rayleigh's G. Sometimes in exam you'll be given some electromagnetic wave. You might be asked to find one that have the highest frequency. So with this arrangement, you will know the order to which the frequency is being arranged. Okay, so please take note of that. So the highest frequency here is gamma ray. Now the frequency actually increases downward. Remember, from the formula we have of wave velocity, we know that wave uh, is lambda f, right? So if I should make frequency subject, your frequency is going to be equal to v all over wavelength. So that simply means that frequency is inversely proportional to wavelength. So what does that actually mean? It simply means that, okay, if gamma ray should have the highest frequency, at the same time gamma ray has the lowest wavelength, okay? So any wave that has a very high frequency means it has a low wavelength. High frequency is associated with low wavelengths, okay? So if that is well understood, as we look at, let's now talk about the next classification, that is progressive and stationary wave. So a wave is either classified as progressive or stationary, and now of course, as the name implies, okay, every progressive wave is continuous, right? Continuous from the source. It doesn't return back to its medium, okay? It's continuous. So if I want to represent a progressive wave, simple, I will represent this by this graph, okay? So which simply, this arrow shows that since it doesn't return back, okay, it's continuous. This is progressive wave. But this is actually opposite to stationary wave. In fact, a stationary wave is made up of two opposing waves, all right? Due to probably a wave going to meet an obstacle in its path, all right? It will generate an opposite wave that travel in opposite direction. So a stationary wave is made up of two waves, two identical waves, two identical waves. Traveling in opposite direction. Traveling in opposite direction. Alright, so now our stationary wave is actually very possible, okay, from a progressive wave if this progressive wave comes to a point where it hits an obstacle. So let me redraw this. Let me show you, okay, how a progressive wave actually look like. Please pardon me, stationary wave. All right, so basically it has to do with a stationary wave generator whenever there is a, let's say, obstacle, okay, two boundary that a wave actually flow in between. So let's say how a wave flows from one boundary, okay, to the next boundary. Let me do it that way. Okay, so as it reaches this boundary, what happened? It reflects, it moves in opposite direction, okay, in the same pattern but in opposite direction. All right, so I can draw that well. Okay, this is just an illustration. So this is actually stationary wave, okay. So there are two opposite waves, one vibrating upward, then the other vibrating downward, right, due to these two obstacles. So this is what is regarded as stationary wave. This is stationary. Now anytime stationary wave is being generated, the point, okay, that particular point where the two wave, or this main point, right, the main point is known as the node, right, where that reflection actually takes place, while the maximum point is known as the antinode. The main point, right, the point where the two wave, okay, originates is the node, while the maximum displacement, okay, at this point is the antinode. So probably let me illustrate it. Just let's say I have just a vibration, okay, of this nature, okay, about the mean position. Right, so this is going to be node, and this is the antinode. So you discover that the antinode is this distance, okay? So since this wave is half cycle, the distance between the node and the antinode, right? The distance from here to here is always quarter wavelength. Remember, for node to node, right? If you see in this diagram here, for node to node, this is just half cycle, right? Of course, this is just half cycle. So half of for node to node is half cycle. Node to node, okay? So it's half cycle, and of course, the distance, horizontal distance for half cycle is just is one wavelength divided by 2, okay? One wavelength is for one cycle, all right? So since in terms of okay, half cycle, right? That's gonna be lambda over 2. Then from node, okay, to antinode. From node to antinode, right? The wavelength will now be gonna be one wavelength divided by 4. So why am I going actually into the details and illustrating all these basic concepts? Because wave is actually not just what I'm doing here is an introduction to wave. Okay, wave have different topics in it. We have sound wave, we have light wave, we have reflection. So this concept are very important, so that subsequently, okay, they will not be sounding very strange. So you need to know them, take note of them, okay? Because as we progress in studying wave, right, you will actually get to hear them again, right? So please take note of that as we proceed. Now we are now going to the last classification of wave. I hope you're still with me. So which of course we can classify wave as a transverse wave. Excuse me. Transverse wave, or is a longitudinal wave. All right, so now a wave is said to be transverse. All right, a transverse wave is so called because, all right, both the material medium, okay, because a transverse wave is so called transverse, all right? It's called transverse wave. Why? Because the vibrating particles and the material medium actually move in opposite direction. Remember, anytime you disturb a wave, okay, what actually transmits the energy is the vibrating particles vibrating. Are you okay? While the medium also has its direction. So when the medium, okay, and of course, and vibrating particles, the vibrating particle, the particle that actually creates the ripples, right, are perpendicular to each other, right, propagate in a perpendicular direction, then such wave is transverse wave. Okay, so a typical example is the example I gave you about the stop water okay, molecules that actually create a wave that goes up and down. So of course the water, let's say the water is just horizontal, so by creating this disturbance, you're going to see the particles vibrate up and down, and that is perpendicular, right? So such is a transverse wave. So this water ripples, okay, is one example. Okay, of course you can also create another form of a transverse wave when you fix string, let's say in form of guitar string, okay, at two fixed point, then you now pluck it. All right, when you pluck it, remember the string will actually vibrate, okay, up, down, which is of course is perpendicular to the alignment of the string, okay, when it is not disturbed. Such is also a transverse wave. Now it also should interest you to know that all electromagnetic wave are transverse wave. All right, so please take note of that. Okay, then of course a wave is either transverse or it is longitudinal. So this opposite of transverse is longitudinal. Okay, so in longitudinal wave we know that both medium, okay, and particles and the vibrating particles all right travel in the same direction, or actually align align in the same direction, okay, or in the same direction. Okay, okay, so a typical example is propagation of sound in air. I told you that anytime you actually speak, all right, to someone, and of course in an environment, okay, in as much as what actually transmits that sound is actually air. So when sound is actually being spoken in air, okay, it actually transfers the sound. How does it do that? By actually compressing the air, and of course spreading out the air particles, right? So there's a region where the air particles actually compresses. There's a region where it actually spreads out. So the will I call it the sequential compression and refraction of air particles, okay, in the direction of the propagation of the sound is the mechanism through which sound can actually travel through air, okay, from the source to its of course a listener. All right, and such movement is longitudinal. Why? Because both the vibration of the air particles, okay, goes in the same direction with the sound, so we call longitudinal wave. Okay, so it's either a wave is transverse or a wave is longitudinal. So this I hope and I believe that so far so good. These terms are actually they are very simple, okay, to comprehend, and I believe that you must have actually taken down one or two important concepts, okay, out of this tutorial. So I will urge you to go through this video again because we're still gonna continue. All right, but then I will give you the time to go through the video again. All right, see you in the next video. Thank you very much.